Right. So now we're going to construct symplectic methods from Hamiltonian splittings. So you might ask, well, what do I mean by Hamiltonian splittings, right? And it comes from the following sort of point of view, which is that, say you have a Hamiltonian vector field and you try to apply splitting to it, right? So there's no guarantee that if you take a Hamiltonian vector field and write it as the linear combination of two vector fields, that, that individually it's like those vector fields are Hamiltonian. So what you should consider doing instead is that instead of splitting at the level of the vector field, you might want to split at the level of the Hamiltonian. Okay, and if you were to split at the level of the Hamiltonian, then of course their corresponding vector fields are again Hamiltonian. And so then you can apply a splitting approach, but by splitting the vector fields by the Hamiltonian. Okay, so let's see how you go about doing this. So let's say that you have a Hamiltonian H, okay, and you can write this as some, sum. It's like of other Hamiltonians, Hi, okay, and the Hamiltonian flows associated with each of these HIs, right? Phi HI of t. So I mean, it's like I'm abusing the notation. It's like which we sort of developed slightly by sort of putting just HIs there. But if you want to think of it in terms of the vector fields, then I would have x sub hi here. Okay. Anyway, so from I equals to 1 to k, all right, associated with the flow, or with the vector field given by just j, it's like gradient hi. Okay, of course that's just the Hamiltonian vector field associated with the Hamiltonian hi, right? Can be computed explicitly. So basically, what I'm assuming is that you have a Hamiltonian, it's like which can be decomposed into other Hamiltonians HIs, such that individually, it's like each of these HI generate a Hamiltonian vector field whose solution flow can be computed explicitly. Okay, so if you're in that setting, it's like then the following is true. Okay, so the theorem is that if H is H1 summed up to HK, right, is any splitting of H, right, then the composition method, which is the composition of these flows, right, is a consistent discretization. Which is to say that it's at least first order accurate. Okay, furthermore, because the exact flows of these small pieces of the Hamiltonian, if you will, right, since these things, right, are symplectic maps, and my composition method is a composition of symplectic maps. It follows that this composition is a symplectic map. So what the take-home message, if you will, is that if you start a Hamiltonian system and you somehow conspire to write that Hamiltonian as some combination of Hamiltonians hi, right, from I equals 1 to k, for example, and it turns out that you can exactly compute the Hamiltonian flows associated with each of these hi's, then when you take this composition, it's like you get a method which is at least first order accurate, and furthermore, it's like that composition of symplectic maps again gives you a symplectic map, and so then you have a numerical method which is symplectic. So that's sort of a relatively easy idea for constructing symplectic methods from these Hamiltonian splittings, and of course the challenge is to find a splitting, it's like which whose component flows it's like you can compute exactly. Okay, but there's an important class of problems it's like for which it's like that's possible. So let me sort of illustrate that for you. And that's the case of what are called separable Hamiltonian systems. So I'll try to explain what that means and then see what happens. Okay. All right, so you have a splitting method for separable Hamiltonian systems. So what does it mean for Hamiltonian to be separable? So you assume that HQP is separable, okay, which basically means that you can write HQP as sort of two separate terms, one of which depends on Q and one of which depends on P. And oftentimes that decomposition corresponds to a kinetic potential energy split. So Tp plus Vq, where T is the kinetic energy, and this is the potential energy. Okay. All right. Then by the theorem which we had, right, the composition of the exact flows, let's call that H1 and H2, if you will. Okay. Right, and if you prefer, you can write it in terms of these kinetic and potential energy terms. Right. It's a first order splitting method. Okay, so let's see what happens. Okay, so we need to compute these flow maps exactly. The flow map for the kinetic energy piece looks like the following, right? So it's the solution of this differential equation, Q dot is equal to the gradient respect to P of Tp, and then P dot is equal to 0. Okay, and then the flow map for V, right, looks like the following. You have Q dot is equal to 0, and then P dot is equal to minus the gradient respect to Q of V Q. All right. So anyway, so you can easily convince yourself. Well, it's like P dot is equal to 0, so P doesn't change. So P of H is just P0, and then Q of H, right? So if P is constant, then the gradient of T, it's like evaluated at a point, is again a constant. So Q of H then becomes Q0 plus H times the gradient evaluated at P0. Okay. All right, and we can do something similar here, right? So Q of H equals to Q at time 0, and then P at H, right? So okay, so Q is a constant. So again, this thing on the right-hand side is a constant. So P of H is equal to P at 0 minus the gradient of V respect to Q evaluated at Q0. Okay, so then you can look at the composition of this. Then you can check that this composition is given by the following. Okay, that Qn plus 1 is equal to Qn plus h times the gradient respect to P of the kinetic energy piece evaluated at Pn plus 1. And then Pn plus 1 is equal to Pn minus h, the gradient respect to Q of V evaluated at Qn. Okay, which is the symplectic Euler method. All right. Okay, so that's sort of a nice example. It's like just to illustrate this idea of, instead of splitting the vector field directly, you split the Hamiltonian, and then you look at the associated Hamiltonian vector fields associated with each of the pieces of the Hamiltonian, and then again you sort of try to compute the exact solution flows, and then compose it to get one of these sort of splitting type methods, and it is automatically symplectic because these are individually Hamiltonian flows, it's like which are symplectic, and so the composition, it's like of them is again symplectic. Okay.